Elasticity and its applications. Elasticity is the ability of a deformed material body to return to its original shape and size when the forces causing the deformation are removed. A body with this ability is said to have elasticity. Elastic region is the region where the material can be deformed and when released will return back to its original configuration. A material's elastic limit is the greatest stress that can be applied to it without causing plastic deformation. The region in which material deforms permanently is called plastic region. The degree of tension or stress at which something breaks is called breaking point. Elasticity. So now let us look at some of its applications. The principle of elasticity is used while designing the ropes of crane. A crane is used for lifting heavy loads from one place to another. It has thick metallic rope to which the hook is attached. The required diameter of the rope is decided by the elastic limit of the material of the rope and load to be lifted. So now let us take an example. Suppose the material of rope is steel. The weight to be lifted is 10 raised to power 4 kg. The maximum stress the rope can hold is 3 into 10 raised to power 8 Newton meter per second square. Therefore, stress should be greater than equal to the elastic limit. Stress is equal to load to be lifted upon area of cross section at the rope. So from the given equation, we get that the area of rope should not be less than 3.3 into 10 raised to power minus 4 meters square. In order to provide a safety factor of 10, the breaking stress is equal to 10 raised to power 5 kg. So now let us take an example. The principle of elasticity is also applicable in making flyovers. A bridge should be designed in such a way that it should not bend too much or break under the load of traffic. We should use the material of large Young's modulus and increase the thickness of bar rather than the breadth. But on increasing the thickness too much, the flyover will bend from between. This is called buckling. To avoid this, a compromise between breadth and thickness is made by using eye-shaped steel cutters. After many years, the bridge loses its elastic strength due to continuous stress and strain, and such bridges are declared as unsafe. But on increasing the thickness too much, Archimedes' principle and its applications. Archimedes' principle states that the upward buoyant force that is exerted on a body immersed in a fluid, whether fully or partially submerged, is equal to the weight of the fluid that the body displaces, and acts in the upward direction at the center of mass of the displaced fluid. Archimedes' principle is the laws of physics fundamental to the fluid mechanics. Archimedes' principle and its application. Certain group of fishes use Archimedes' principle to go up and down the water. To go up the surface, the fish will fill its swim bladder with gases. The gases diffuse from its own body to the bladder and thus make the body lighter. This enables the fish to go up. To go down, the fish will empty their bladder. This increases its density and therefore the fish will sink. Certain The Archimedes principle is also applicable on FLIP, Floating Instrument Platform. This is a research ship that does research on waves in deep water. It can turn horizontally or vertically. When water is pumped into stem tanks, the ship will flip vertically. The ship pumps water in or out of tank to rise or sink. The Archimedes
Since ancient times, scientists have been studying the motion of celestial objects like sun, planets, moon, etc. Contributions of Brahe and Kepler. To test the validity of Copernicus' model, the great Danish astronomer Tycho Brahe made extraordinary observations by studying the motions of planets and stars without the aid of a telescope. His data were critically analyzed over a period of 20 years by Johannes Kepler, who was Brahe's assistant. From these complicated data, Kepler deduced simple relations that governed planetary motion. These are three famous laws of Kepler, which strongly supported the Copernicus model of solar system and played major role in the discovery of Newton's law of gravitation. Kepler's The point on the orbit closest to the Sun is called perihelion, and the point on the orbit farthest from the Sun is called aphelion. Second, law of areas. The radius vector drawn from the Sun to a planet sweeps out equal areas in equal intervals of time. That is, the areal velocity of a planet around the Sun is constant. Suppose a planet takes same time to travel distance A and B. From Kepler's second law, the areas A and B covered in equal time must be equal. Clearly, the planet covers a larger distance A when it is near the Sun than B when it is farther away in the same interval of time. Hence, the linear velocity of a planet is more when it is closer to the Sun than its linear velocity when it's far away from the Sun. Kepler's laws apply to any celestial body orbiting any other celestial body, any planet around a sun, the moon around the earth, any satellite around the earth, the International Space Station, any rings around any planet. Later, Isaac Newton built upon Kepler's laws to confirm his own law of gravitation. If it wasn't for Mars and its complicated travels across the night sky, Johannes Kepler may not have derived his laws of planetary motion. Isaac Newton might not have had foundation for his law of gravitation. The red planet Mars is forever linked to our understanding of the solar system and one of the basic forces of nature.
Newton's law of cooling. In the 17th century, Isaac Newton studied the nature of cooling. In his studies, he found that if there is a less than 10-degree difference between two objects, the rate of heat loss is proportional to the temperature difference. Newton applied this principle to estimate the temperature of a red-hot iron ball by observing the time which it took to cool from a red heat to a known temperature, and comparing this with the time taken to cool through a known range at ordinary temperatures. According to this law, if the excess of the temperature of the body above its surrounding is observed at equal intervals of time, the observed values will form a geometrical progression with a common ratio. However, Newton's law was inaccurate with the high temperatures. Some real life applications of Newton's law of cooling. So, Newton's law of cooling can be used to predict how long it takes for a hot cup of tea to cool down to a certain temperature, or it can be used to find the temperature of a soda bottle placed in the refrigerator by a certain amount of time. Forensic experts use Newton's law of cooling to find out when victims of crimes died. They take the temperature of the body when they find it And by knowing that the average temperature of the human body is 98.6 degrees initially, assuming that the dead person wasn't sick, and measuring the room temperature, they can find the K and then find T. And this is how they can find the time of the death by using differential calculations and equations.